One of the things that you have to get used to in this course, and you'll see it on past midterms and past final exams, is that we have different types of coordinate systems. We're trying to describe things in the coordinate system that seems optimal for the problem we're dealing with. And one of the more used coordinate systems and the most intuitive, I think, in a lot of ways is rectangular coordinates or Cartesian coordinates. And the goal here is to look at motion using rectangular or Cartesian coordinates. So I have a particle that's traveling along some sort of path, and here's that particle. You can see that yellow line corresponds to the path. The cube is the particle of interest. And I can define its distance with regards to distance along the x direction, like this, which is this one, distance along the y direction, which is here, and distance along the z over here. And if I do that, I have a position for that particle instantaneously. And that position can be defined also in terms of r. And r is something that we'll use a lot as a positional a method of defining position. And the other thing I can do is not use x, y, z. I might use rx, ry, rz. So my position is r equals xi plus yj plus zk, or r equals rxi plus ryj plus rzk. And in that case, what I've done is I've also used unit vectors I, j, and k to define direction. Unit vectors have magnitude 1, and they point in the direction I'm interested in. So that allows me to write this term, which is a vector which has magnitude and direction, in terms of the magnitude component and the directional component. It also allows me to break up equations so that I only look at the x direction, y direction, and z direction if I have to solve for multiple cases. V, as usual, is tangential to my path, and V needs to be calculated using the chain rule. So V equals dr dt, which is dx dt I. Okay, that's good. All right, x di dt, dy dt j plus y dj dt, dz dt k plus x dz k dt. Now, if you do that, these terms look kind of funny, these unit vector derivatives. But they go to 0 because they never change direction and they never change magnitude. It's always unit vector 1, and it always points in the same direction as the particle is traveling along its path. So my velocity is equal to dr dt, dx dt, dy dt, dz dt in the I, j, and k. So total is just going to be velocity equals dr dt equals vxi, vyj, vzk, where I know that these correspond to these terms over here. And I can do something where I say x dot, y dot, z dot, and if I do that, I have, say, an x dot, which is really just dx dt. And I then can say v equals the magnitude of v, the speed, if you wish, is going to be vx squared plus vy squared plus vz squared square rooted. If I want to know the direction of the velocity, I take the velocity and divide it by its magnitude, and that's the speed. So it's vxi, vyj plus vzk over v, which tells me what direction when I normalize it. It's essentially creating a unit vector because this is equal to 1 after the normalization. Acceleration, as we mentioned, or as I mentioned before, is not necessarily going to point in the direction of motion or in the direction of the path. In fact, most times it doesn't. And so I end up with acceleration, which is equal to v axyi dv dt axi ayj azk, or x double dot I, y double dot, j, and z double dot. And all that is the second derivative of whatever variable of interest with respect to time. And I should just put that correctly, and it's there. Magnitude, same thing. I normalize the acceleration by the magnitude of acceleration. I get the direction. Magnitude of acceleration is the square sum, square rooted, of the component terms. So curvilinear motion changes both magnitude and direction of position, velocity, and acceleration. The velocity vector is tangent to the path, and the most important thing, acceleration is usually not tangent to the path. Rectangular vectors do not have a change in unit vector direction, so they become easier to deal with than other coordinate systems, which probably is something that I'm sort of waving a big red flag as you kind of expect something will happen in the next lecture.